Bonjour, ça va? Je m'appelle Courtney, and today we're going to be talking about Standard 7, which for us is equilibrium. So equilibrium is the condition which occurs when the concentration of reactants and products participating in a chemical reaction exhibit no net change over time. So the standards specifically are set into two different groups, dynamic equilibrium and the position of equilibrium. So for dynamic equilibrium, we're going to outline the characteristics of a chemical and a physical system. And then, for the position of equilibrium, we're going to talk about equilibrium constant expression, which is K sub C, for homogeneous reactions. Then we're going to apply Le Chatelier's principle to predict effects of temperature, pressure, and concentration on the position of equilibrium, and the value of the equilibrium constant. Then we're going to talk about what effect does a catalyst have upon the equilibrium position and its equilibrium constant. And finally, we're going to apply the concepts of kinetics and equilibrium to industrial processes, such as the production of ammonia and H2SO4, which is hydrosulfuric acid. Ugh. So the reaction that we're going to be using for an example of equilibrium in a physical system is the reaction of bromide in liquid state yielding bromide in gaseous form. So bromine is placed in a container at room temperature. And we know bromine is a volatile liquid that has a boiling point at room temperature. And the particles will have enough energy to escape in vapor form. But at the same time, the vapor molecules will also collide, creating more liquid through condensation. So at this point, equilibrium would be the rate of evaporation when it is equal to the rate of condensation. So going back to the reaction, we notice the yield symbol implies that the reaction is occurring and it is going both forward and backward. And going back to the concept, we know that our reaction is at rest, which explains the equal production of liquid bromine and gaseous bromine. Now, if we look at the picture in front of us, we see that in the first box, this is kind of a normal reaction, the rate in which liquid bromide turns into gaseous bromide. But when we go to the right box, we can see that it is at equilibrium, because the rate of the molecules are going into liquid form is equal to the rate of molecules going into gaseous form. For our chemical system, the reaction that we're going to be using for a conceptual example will be iodine reacting with hydrogen, both in gaseous form, yielding hydrogen iodide in gaseous form. So the reaction of dissociation between hydrogen iodide and single elements, iodine releases as a purple gas, but hydrogen and hydrogen iodide are colorless. This allows for us to view the extent of this reaction. If the reaction is in a sealed container, there is an increase in color. And after the increase in color stops, it seems the reaction has stopped. But what actually is occurring is the rate of dissociation of hydrogen iodide becomes equal to the rate of the reverse reaction, and equilibrium was reached. Alright, now I'll be talking about the features of equilibrium and their explanations. So number 1, equilibrium is dynamic. The explanation is the reaction is not stopped, but both the forward and the backward reactions are still occurring. Number 2, equilibrium is achieved in a closed system. The explanation? A closed system prevents the exchange of matter with the surroundings. So equilibrium is only achieved where both the reactants and products can react and recombine with each other. Number 3, the concentrations of reactants and products remain constant at equilibrium. The explanation? They are being produced and destroyed at an equal rate. Number 4, at equilibrium, there is no change in macroscopic properties. Explanation? This refers to observed properties such as color and density. These do not change as they depend on the concentrations of the components of the mixture. Number 5, equilibrium can be reached from either direction. The explanation? The same equilibrium mixture will result under the same conditions, no matter whether the reaction is started with all the reactants, all products, or a mixture of both. So next, we're going to be talking about our equilibrium constant. That's represented by K, lowercase c. And as you can see, I'm writing the general formula, which is where I'm using uppercase letters identified by as the elements, and the lowercase letters being our coefficients. And as you can see, our elements are raised to the power of our coefficients. Okay, so next I'm just going to give a general form of or what a reaction would look like kind of like using those coefficients so we can know where to put what. So our uppercase letters are representing our elements, while our lowercase letters are representing our coefficients. So as you can see in the numerator, we have our products, and in the denominator, we have our reactants. So I'm going to give you guys an equation that I went over that was a representative of our chemical system and a conceptual idea of it at equilibrium. So I'm going to have hydrogen in gaseous form, iodine in gaseous form, yielding hydrogen iodide. And so basically I want you guys to pause the video and try it yourself. Okay, welcome back. So the solution we found is hydrogen iodide raised to the second power, which is indicated by the coefficient, and both of our reactants in the denominator. So now I'm going to give you guys two other equations. The first equation being a reaction between hydrogen in gaseous form plus oxygen in gaseous form, yielding water. And the second equation that I'm going to give you guys is going to be copper reacting with ammonia, both of them being in aqueous form, and them both yielding copper ammonium. So after I finish writing this equation, I want you guys to pause the video and try it yourself. Okay, welcome back, guys. Okay, so the solution for our first equation is going to be water raised to the second power over hydrogen raised also to the second power, and oxygen raised to the first power. And that's going to be our first equilibrium constant. As for the second one, we're going to have copper ammonia raised to the first power because we have a coefficient of 1, and so that doesn't really need to be written, but just for technicality we're going to say raised to the first power. And it's going to be over copper raised to no power, and ammonium raised to the fourth power. And that's our second equilibrium constant. So good job, guys, if you got it right, and if you didn't, try again. Okay, so the next thing we're going to be talking about is Le Chatelier's principle. And Le Chatelier's principle is the idea that a system at equilibrium, when subjected to a change, will respond in such a way as to minimize the effects of said change. So the factors that affect the position of equilibrium are going to be concentration, pressure, and temperature. So now we're going to be talking about the effect that concentration has on the position of equilibrium. So let's just say we have a reaction. If there's an increase in concentration on one side, it causes often equilibrium to shift to the opposite side of where the concentration is increased. Now, if we have a decrease in concentration, this will cause equilibrium to shift to the side where the decrease is in the concentration is occurring. And this kind of goes back to our definition of Le Chatelier's principle, that idea that if there's a change in the system will respond in a way such as to minimize the effect of the change. And so, let's just say we have a reaction. If there is an increase in concentration on the reactant side, there will definitely be a shift to the right. So I want you guys to think for yourselves. What would cause equilibrium to shift to the left? Please pause the video and take a moment to think. There are two answers. Alright, welcome back. So the two things that would cause equilibrium to shift to the left would be an increase on the product side and a decrease on the reactant side. The next thing we're going to be covering is the effect of pressure on the position of equilibrium. So equilibria will be affected by a change in pressure if there's a reaction the reaction involves a change in molecules. This is due to the direct relationship between the number of molecules and the constant pressure at a fixed volume. So if there is a reaction with an increase in pressure, the system will favor the side with fewer molecules. Therefore, a decrease in pressure would shift it to the side of the large amount of molecules. There is a shift in equilibrium position, as I mentioned, but there is no change in equilibrium constant. So for an example, we have a reaction, which is carbon oxide reacting with hydrogen, yielding methanol. So we look at a reaction, and we look at the amount of molecules we have on each side. So see, our carbon oxide is considered one molecule, and a hydrogen is also considered one molecule, but because there is a coefficient of 2, we consider it to be 2 molecules. And then on the other side, we have methanol, which is just one molecule. So obviously, equilibrium will shift to the side that has the smallest amount of molecules, which will be methanol. Now, let's per se we want it to shift to the reactant side. We would just have to make a decrease in pressure. So now I'm going to be talking about the effect that temperature has on the position of equilibrium. And this is dependent upon whether or not the reaction is endothermic or exothermic. Endothermic meaning it is absorbing heat, and exothermic meaning it is releasing heat. So we like to think of heat as a product in an exothermic reaction and a reactant in an endothermic reaction. So let's take an exothermic reaction, So we have nitrogen oxide, and it yields N2O4. So the change in enthalpy is negative 24 kilojoules. And so in this situation, equilibrium will shift to the left, and the equilibrium constant will increase. And this is due to the fact that it is exothermic, heat is being released, so in order for the system to favor the change, it has to shift to the left to add more heat to the system. So for endothermic reaction, we have nitrogen reacting with oxygen forming nitrogen oxide. And the change in enthalpy is a positive 181 kilojoules. So equilibrium will shift to the left, and the equilibrium constant will decrease. So now moving on to the effects of the catalyst upon the equilibrium position and also the equilibrium constant. So the catalyst has really no effect upon those. The catalyst basically speeds up the rate of the reaction by lowering its activation energy, and it increases the number of particles that have sufficient energy to react without raising our temperature. So in the diagram, we see that the effect of the catalyst in lowering its activation, the reaction's activation energy, is the same for both the forward and the backward reaction. Therefore, the rate of both of these reactions will be increased by the same amount, keeping it at equilibrium. The catalyst will therefore have no effect on our position of equilibrium or on our value of Kc, as I've said. The catalyst will not increase the yield of the product in the reaction. But what it will do is it will speed up the attainment of the equilibrium state, causing the products to form more quickly. So now we're just going to review our factors that affect and whether or not they affected the equilibrium constant and our position of equilibrium. Okay, so concentration, it did affect the position of equilibrium, but it had no change on the value of our equilibrium constant. With pressure, it does have an effect on the position of equilibrium, but then again, it only has an effect if there is a different number of molecules on either both the reactant and the product side. So it's kind of going back to that direct relationship between pressure and the number of molecules, allowing for the position of equilibrium to be shifted. And pressure does not have an effect on the equilibrium constant. With temperature, it has an effect on the position of equilibrium and our equilibrium constant. Remember, when it is exothermic, our equilibrium constant increases, and when it is endothermic, our equilibrium constant decreases. And finally, the catalyst, it does not affect the equilibrium constant or the position of equilibrium. It just speeds up the rate of the reaction. So now what we're going to be talking about is the production of ammonia. So what we can gather from our equation, nitrogen reacting with hydrogen producing ammonia that has a change in enthalpy of negative 93 kilojoules. So we know that all the reactants and products are gases, and there is a change in the number of molecules as the reaction proceeds. There are 4 gas molecules on the left side and 2 on the right. The forward reaction is exothermic, and so it releases heat. The backward reaction is endothermic, and so it absorbs heat. So applying Le Chatelier's principle, we can therefore consider that the concentration, the reactants nitrogen and hydrogen are supplied in the molar ratio of 1 to 3, and so the product of ammonia is removed as it is formed, and this helps pull the equilibrium to the right, increasing the yield. And so with pressure, as the forward reaction involves a decrease in the number of molecules, it will be favored at a high pressure. Okay, and for temperature, the forward reaction is exothermic, and it will be favored by the lower temperature. And finally, with the catalyst, although our catalyst does not affect the yield of our ammonia, it speeds up the rate of the production, and it helps to compensate for the moderate temperature that we're using. And so a catalyst, finely divided iron, is usually used for this production of ammonia, and small amounts of aluminum and magnesium oxides, and this adds to the improvement of its activity. Okay, so thanks for watching my video, guys. I hope you enjoyed it, and I hope you gained something from it as well. Au revoir!